Good afternoon, everyone, and welcome to this year's third Scarlet Lecture. Today's featuring Dr. Nathan Freed, Assistant Teaching Professor in our Department of Biology. My name is Howard Marcatello, and I serve as the Dean of the Faculty of Arts and Sciences, Camden. Together with the Office of Alumni Engagement and Annual Giving, it is our pleasure to present this series, which gives a platform to our faculty to share the research with a wide audience. Despite the difficult year, we have offered 3 Scarlet Lectures since September and have plans for many more in the next academic year. Today's lecturer is Dr. Nathan Freed, Assistant Teaching Professor in the Department of Biology. Dr. Freed's research focuses on the mechanisms behind how sleep disruption impacts chronic pain. For the past 10 years, he has used modern neuroscience techniques to tease apart the circuits and molecular mechanisms behind the development of chronic pain and migraine. Alongside his research, he also focuses on training first-generation, low-income undergraduates and other students from underrepresented backgrounds to launch successful scientific careers. This afternoon, Dr. Freed will present how the body language of a mouse may help us find pain medicine that's safer than opioids. As you may be aware, chronic pain affects nearly a third of the US population. A major contributing factor to the opioid epidemic is the lack of safe pain therapeutic alternatives. But the pain research field has had significant challenges finding new ways to treat pain patients. Some have thought this is derived from inconsistencies in research methods used to test new drugs in animal models. Dr. Freed will discuss the intersection of chronic pain, the opioid epidemic, and how we're improving computational neuroethological tools to advance translational pain research. Today's talk will be followed by a question and answer session, and during the talk, you're welcome to enter questions in the Q&A, and we'll get to those at the end of Dr. Freed's talk. Again, thank you everyone for logging in today, and please join me in our virtual welcome of Dr. Freed.
All right, it is great to be here. Let me just share my screen really quick. Okay, everyone can see my screen and hear me? Good, cool. So thank you so much. Again, my name is Dr. Nathan Freed. I'm an assistant teaching professor here at Rutgers University Camden in the Department of Biology. And today I wanted to talk a little bit about a story that we've been working on for several years, really trying to improve the way, not necessarily of finding a new way to treat pain patients, but improving the way that we actually study pain. And if we can improve the way that we study pain, we can increase the chances that we're actually going to stumble on that really important pain therapeutic that can address the opioid epidemic by providing an alternative to using opioids to treat certain forms of chronic pain. So how the body language of a mouse may help us find new pain medicine that's safer than opioids. And again, my name is Dr. Nathan Freed, and it's really an honor to be part of this Scarlet Lecture Series. I think it's a great chance for faculty members who are doing research on our campus to reach out to a wide audience, to reach out to our community, and then to really connect. And even though during this time we've been really disconnected in this virtual environment, I think that these virtual spaces also just allow us to be able to reach a larger audience. So for all of you who are here today, welcome and thank you so much for being here. And again, it's an honor for me to be part of it. Thank you so much to the College of Arts and Sciences for inviting me to give this lecture. So the first thing I want to start with also is that a major thing that I'm very interested in is working with Rutgers Camden students, because Rutgers Camden students, they reflect this heterogeneity of backgrounds of students, a lot of non-traditional students, which is what I come from too. I come from a first-generation low-income background, and so being part of Rutgers Camden community is really exciting for me. Of the 5,000 undergrads that we have in total, there's 350 undergraduate biology majors approximately. And of those 350 biology majors, 54% of them are first-generation students. 72% of them work off-campus jobs, and 91% of those students are commuting from home. And what that represents is a really unique student population of students who are balancing multiple jobs while trying to get an education, who are truly pioneers in their family, being the first to go off to college. And I think that it's an important aspect to work with students from a range of backgrounds to give them the opportunities that they need to really develop as researchers and scientists so that they can not just, so that Rutgers Camden can evolve not just as a landing pad for a lot of students, but really as a launching pad for those students, especially for my interests, helping them get off to a PhD in the biomedical sciences. So it's really exciting to be here. But if I were to take what I do, what all neuroscientists really do, we say that we study the brain. And you can break this into really two components, two directions that neuroscientists or neurobiologists end up going on here at Rutgers Camden or elsewhere across the world. We're really interested in two things. We're really interested in function and dysfunction. How does the brain work? What is the function of certain parts of the brain? How do different circuits come together to provide the function of the nervous system? And then how does it all fall apart when we have dysfunction? That can be anything from Parkinson's disease, Alzheimer's disease, to traumatic brain injury, to different forms of chronic pain. But ultimately, if we just start to step back and not think about a specific discipline in brain science, you can just break this into two different parts, function and dysfunction. And the field has really gotten really good at answering defined questions that explore the function and the dysfunction. One of the questions is, how is the brain wired? We have really evolved these amazing techniques using viral neuronal tract tracing that allows us to know exactly where a single neuron projects its axons and connects within the brain, especially when we're working in animal models to study these tinier brains to then extrapolate information about how our human brains will work. So we have these really fancy technology to figure out how the brain is actually wired. And another question you can ask as a neuroscientist when we're thinking about function and dysfunction is, how do these circuits actually function? How do they work? Or how do they become dysregulated? And we have very complex and nuanced devices and technologies like optogenetics and machine learning to answer questions along those lines. And then we've also developed really amazing modern neuroscience techniques to ask the question of which neurons are involved in different functions or dysfunctions. So not just what are the circuits, how are they wired, but what are the individual neurons doing within each of those systems. And we use these things called GECIs, or genetically encoded calcium indicator dyes, that allow us to see when an individual neuron is becoming activated during some sort of event or some sort of challenge to an animal. But we've not advanced the ultimate output of all behavioral or all neuroscience research, which ultimately ends up being behavior. So when we have to think and we have to answer the question is, how does the brain actually control behavior? Because if behavior is the output for whatever we're doing, we have very rudimentary and very dated ways to be able to do that. Basically, we watch a mouse and we assume what it's feeling or what it's experiencing, what its internal experience is. So we've made huge advances in the technology that we have to answer really important questions in neuroscience. Yet we are still relying on decades-old methods to analyze the behavior of animal models to make interpretations about human health. So there is this big movement in the field. In the past couple of years, there's been this call to action for computational neuroethological methods to analyze behavior. What does that mean? That just means basically trying to find more discrete and reliable methods to analyze the ultimate output in neuroscience, the behavior, so we can make better interpretations. Because we're not doing that as a field at large. And each subdiscipline also has its own challenges when it comes to this. And so there's a number of undergraduate students that I work with, Brittany, Sarah, Gilharia, Kiyoshi, Megan, Bobby, Sherrick, Ubeda, and Jenny on our campus to drive the pursuit of answering these questions, of trying to improve the methodologies that we have with this. And to frame this overall problem, like if I were to say that there's a problem in neuroscience, it's that we're not using behavior in the most accurate way. But to frame this, I have a story today to tell you about how we've addressed that, at least in the chronic pain world. This is a wonderful image that's done by Sarah in my lab, who's an undergraduate here at Rutgers Camden Biology. She made this portrait, a self-portrait of the own chronic pain that she experiences. And I think it really captures sort of this internal experience that somebody has when they're suffering through chronic pain. And it frames what we're really struggling with as a nation, as a whole world, really, because 100 million individuals in the United States are suffering from some form of chronic pain. That can be everything from lower back pain to severe headache, migraine pain, neck pain, facial pain. That's more than diabetes, heart disease, and cancer combined. And although this condition doesn't necessarily lead to death, there's no mortality that's based on chronic pain. What we can say, though, is that this suffering leads to 91 Americans dying every single day from an opioid overdose, because a major go-to way to treat chronic pain is opioids. That they work, they've worked for decades, they've worked for centuries. They're not always the go-to, but they are a critical way for us to be able to treat certain forms of chronic pain. And 91 Americans are dying each and every day from this opioid overdose. Nearly half of them, is from a prescription opioid. And I want to also step back and kind of framing this, because we can see that chronic pain is a problem, is its own epidemic, and we can see that the opioid epidemic is its own problem. But it's really important to emphasize really the history of how this opioid epidemic really began. And the CDC really identifies, and our field identifies, three major moments in this opioid epidemic. First, in the 1990s, when there was a rise in prescription opioid overdose deaths. We can see that actually right here. In the 90s, we started seeing an increase in the number of people who were dying from the commonly prescribed opioids for pain relief. But really in 2010, we started to see this really big peak in the number of individuals who were dying from heroin overdose deaths. And then later on in 2013, we really started to see this really stark increase in synthetic opioids, primarily fentanyl, as it was introduced onto the market. And so we have this multifaceted opioid epidemic that has multiple things that are contributing to the rise in opioid overdose deaths. And so I say this because I want to frame that there's this persistent challenge that the pain field needs to attend with. One is that, we need to move away from opioiphilia, meaning a love of opioids as the primary way to treat pain patients, because that can lead to an increase in addiction and death, as we saw in the 90s. But we also need to make sure that we understand and recognize that it's not just chronic pain prescription of opioids that's contributing to this opioid epidemic. We have issues with heroin, we have issues with other synthetic opioids, and of course, socioeconomic issues that are contributing to the challenges that we see at this opioid epidemic. So if we become very afraid of opioids, what that can inversely do and problematically do is it can limit patient access to medicine that is the only medicine that can actually restore common day-to-day activities for some individuals. Where no other drugs or pain analgesics are working, opioids are basically the last line of defense to help patients. So if we are too afraid of opioids, we're limiting patient access. We're also stigmatizing the use of opioids to treat chronic pain or to treat pain in those patient populations that rely on that. So for passing legislation, because we're very, very afraid of it, to limit its access too much, making it too strict, it's hard on the patients. But of course, if we then move too close to saying, well, let's just keep on using opioids for every type of pain condition, then we end up having another problem, which is, increasing addiction and deaths across the United States and across the world. So it's finding this great balance between these two different ends of this pendulum to really find the most effective way to be able to address this opioid epidemic. So really, though, as a researcher, there's two things that we can really do right now to address the opioid epidemic from a chronic pain perspective. One is we can find opioid alternatives. So that can be anything from cannabis to acupuncture to massage therapy or other analgesic compounds that are in development. Find something that works just as well as an opioid for those patients who need opioids so that they can move away from opioids, or redesign the opioid. Take that opioid and chemically modify it so that it relieves pain, but it doesn't contribute to addiction. And there's been a number of research studies that have demonstrated that that is a possibility, that you can basically design an opioid that is safer. And so all of this has to start with basic science. It has to start in an animal model where you test a new therapeutic. You say, hey, I got a good idea. This works on this one particular mechanism. Let's test it to see if we can bring it to clinical trials for humans. And so that first step is you have to test that in an animal model. And the question, though, that you can then ask yourself is, as a pain researcher, as a neuroscientist, as a behavioral neuroscientist, how do you know that that pain therapeutic is actually working in that animal? And we can step back and we can ask the same question of humans. How do you know a pain therapeutic that you give to a human is actually working? And I say that they tell you, they actually try to tell you because they can speak to you. We have, a scale of 0 to 10. We have facial images here or like cartoon images. We have different languages. You can tell a clinician, hey, my pain is at a level of 5, and now it's down to a level of 3 after giving that pain therapeutic. They can convey that. But there's challenges even in that because it's very subjective, that experience. So my pain level of 5 might be completely different than your pain level of 5. So it ends up becoming a challenge even when we're working with humans. So then you go back to the mouse. The mouse can't speak, right? They're not non-verbal species. They can make noises and they can do different things, but you can't say, hey, how is this pain therapeutic? Did it get rid of your headache? That's not going to work. So at the end of the day, you have to rely on behavior. If you remember that first slide, this is really going back to this idea that we need to have really, really exact ways to measure that behavior so that we know what the ultimate outcome of a therapeutic that we want to test is in that animal model before we bring it to humans. So how do we actually do this? How do we know an animal is in pain? They can't tell you, but we can use 3 behavioral classes, assay classes. Assay is just a term for experiment, a type of method to be able to assess the behavior of an animal. The first of which, the first category that we can use is reflex-based assays with the paw or tail. We can take something called a ventre hair or some other mechanical stimulation, and I can poke the animal. And the animal responds. It goes, hey, why'd you just touch me? And if the animal responds more often than it doesn't, than normal, then you can say, hey, that animal is more sensitive to that poking of them on their paw or on their tail. So the animal must be in a state of pain. We would make that assumption. The second one is operant-based assays. You can allow the animal to experience 2 different environments, 2 different assay chambers, and you can expose them to either pain-inducing manipulation or pain relief manipulation, if it's a therapeutic, in one of the chambers, and you do that over the course of a few days, and then you come back, you put that animal back into that chamber on day 5, and then you let the animal choose where does it want to spend its time. If it has experienced pain relief in one of the particular chambers, it's going to spend more time in that chamber because it's going to say, hey, I think that I enjoy what occurred here or relieve my pain. So you can make the interpretation that whatever you did in that particular chamber was something that was relieving the animal's pain. The third way that you can do this too is just pain-related behavioral spontaneous behavior analysis, where you literally just sit back, you cross your arms, and you just watch the mouse. You just watch them running around. You look at their behavior. How does it change? Is there unusual arching of the back? Is there shaking or licking of the paw? Is there guarding the paw? Is there weird vocalizations that are occurring? You're not doing anything to the animal. You're just watching them. You're just trying to see, like, do they look like they're in pain? You can imagine that there's a lot of open subjective analysis to that type of assay class. But ultimately, most people use the reflex-based assays with the paw or tail because they're simple, they're straightforward, and you can do them pretty quickly. You can train a lot of people to be able to do them. It's not too challenging to do these assays. But when we actually look at the success of finding a new pain therapeutic, we have a 2% success rate of finding a drug that works in an animal, that we say, hey, this is a drug, we should definitely invest the millions, the multi-millions of dollars into bringing it to clinical trials. We have a 2% success rate of bringing a drug that we think is working in an animal and then having it ultimately be a successful drug that can help pain patients. 2%. It's an abysmal success rate. And fair enough, though, if you look at all other diseases, all other drugs, generally there's a 9.6% chance that you're going to have a successful drug that you just developed. Whereas in pain, it's 2%. So we got to step back and ask, what is happening here? What is happening in the pain world that when we find a drug and we're like, hey, this is a really, really good candidate, let's test it in humans. Why is it that 98% of the time we're completely wrong? We're missing the target with this. And some in the field are saying maybe it's because the behaviors that we're analyzing, these decade-old behaviors, the decade-old assumptions of the behaviors that we're assessing have some sort of critical flaw to them. And if you look at these reflex-based assays, you look at the data, you can start to extract potential problems. And we've categorized these into 3 different problems. One is that there's a binary output to this. When I poke an animal with something that might be sharp or a little pinprick to see if they felt the pinprick or if they're more sensitive to the pinprick, versus touching them with like a brush, my output is still just, did the animal move? Did the animal feel that? And so you can see right here in a paper in 2015 on the left-hand side, paper in 2015 on the right-hand side, this is a brush, just sweeping a brush against the animal's paw. All I'm measuring on the y-axis is whether or not the animal responded to it. And on the y-axis for the pinprick, I'm also only responding or measuring whether or not the animal responded to it. So like, did the animal feel it? Yes or no? And if I'm using the yes or no aspect of a response that's from two completely different types of stimuli, then it might not necessarily be providing an accurate representation of the internal experience of the animal. Second one, assays rely on the subjective human assessment of stimulus quality. When I use a brush on an animal, that is considered a touch assay because I put a brush on my skin, it doesn't hurt. Why would that hurt? Pain assay, I take a pinprick, I poke a pinprick, I say that hurts for me, so it must hurt for the animal. But maybe the animal, since it's a mouse is a prey species, maybe that brush actually does induce a little bit of sensitivity or pain because they're more on edge. Maybe when I press that brush against its skin, it's feeling the same type of pain as if I had sunburnt skin and I put a brush up against my skin and it would send like shivers down my spine because it's so painful. Third one is that, oh, I already revealed my cat gifts. Dang, a little bit too early. A high rate of response does not mean there's a high intensity of that particular assay. So this is sticky tape. I take Scotch tape, put it on the animal's paw, and I pull it off, and then the animal responds. And we can see that with the brush, with sticky tape, with pinprick, we're getting pretty high response rates to the stimuli, but they're not indicative of the actual intensity of the stimulus. So if I'm trying to figure out if an animal is experiencing less sensitivity or less pain once I give them a therapeutic, relying on these reflex assays, these yes or no assays, can be rather uninformative to the extent that if I touch an animal's paw, a cat's paw, and it just doesn't like that, it moves its paw away, it's like, no, don't touch me, versus this animal over here, I touch its paw and it freaks out. What we need to do with this type of assay is to hone in not necessarily on the stimulus or the presence or absence of a response, but instead the quality of the response. The quality is what's going to be able to provide us much more information. And so given that reflexive-based assays are so widely used in the pain field, the question that we had for this story is, can we improve their reliability so that when we find something that works in an animal, we can be a little bit more sure before we bring it to clinical trials. We don't have to waste millions of dollars pursuing things that are not going to inevitably help pain patients. And so this led to a paper in the summer of 2019, development of a mouse pain scale using subsecond behavioral mapping and statistical modeling. I did much of this work over at the University of Pennsylvania when I was a postdoc, and then finalized some of the work when I was here in the beginning stages of my faculty position here at Rutgers Camden. It's been picked up by a lot of press because the field itself has recognized that it is an impactful way to start to reassess the way that we're actually performing our analyses on pain behavior. And this is in collaboration with Drexel University, Rutgers, New Brunswick, and Johns Hopkins University. And I'm just going to walk you through a little bit of this work that I did for this particular study. So we wanted to revisit that withdrawal. We wanted to look at those cat gifts and say, well, what could we learn? How could maybe we could increase the way that we're analyzing this response. And so just as an example, we can look at the response of a mouse in a restrainer, one tiny mouse, a CD1 mouse, adult mouse, and I'm going to take a makeup brush and we're just going to pass it across its paw. And we're going to see, okay, normal circumstances, normal analyses that I would do. I would say, yes, that animal responded. The animal felt that. And maybe the animal feels that and responds 9 out of 10 times. And maybe if they're more sensitive, I'd say that they're responding 10 out of 10 times. But there's so much more to that video than just the animal turning around and responding. So we took inspiration from other fields. One is from the Granado lab over at the University of Pennsylvania, who studies fish and their response to a startle sounds like a beep. And they took their behavior and their movements and they slowed it down. They did slow motion kinematic analysis of their behavior in response to a startling noise. so that they can make conclusions about their world of neuroscience that they're exploring. And we thought there's, it was interesting that they were able to really pick up more nuances to that behavior than just, okay, the animals responded, they moved. They can pick up habituation to the startle response. And again, too, in 2014, other labs started taking those fancy cameras and they started using them to analyze the behavior of fruit flies and beating of their wings as they're flying so they can understand the kinematics, not just to understand how do they do something, but to use that as an output measure for whatever world of neuroscience that they're exploring. So we thought, maybe we could do something similar. So we did that in these animals, and we slowed the movement down so that we could start to see more nuances to the behavior. So we're recording at 2,000 frames per second, and you can see all sorts of information that you could extract from there. The amount of time that the paw is in the air, the speed in which the animal moves its paw, the turning and looking, the changing in ear shape, the changing in the digit shape, the movement of their tail. And we said, there's a lot more information in here than just the animal responded. What could we do with that information? And would it be valuable for us to be able to interpret the internal state of that animal? So once again, we pulled some more inspiration from other groups. This is the Long Lab at NYU that studies birdsong and has identified individual syllables in the songs that birds sing. And they've really tried to extract where, under different conditions, what happens to individual syllables of that sound. The Data Lab in 2015 published a study of saying that actually all animals, in the same way that you have vocalized syllables, you also have behavioral syllables. A full behavior of an animal running around or moving or smelling or experiencing something is going to have different beats that it does to do that full behavior. And so we took that and we said, well, maybe we could find individual beats, individual syllables of this full response, of this full withdrawal response that the animals have. And what that ended up being is a really, really robust analysis of every single frame that occurs in that animal's response to different types of stimuli, both innocuous stimuli and noxious stimuli, so that we could extract what is every single thing that we could possibly measure. And that's really where you start out with. When you're trying to explore this type of thing, it's a little exploratory. You're not sure what you're going to get, but you go in and you try to see what is it that I could possibly measure that's more than just, yes, the animal responded, or no, the animal did not respond. And so we did this in two different genotypes. One's called CD1 animals, and then one's called C57 animals. These are just two different types of strains of mice that are commonly used throughout all neuroscience labs. We also did this in both males and females. And we could look at the movement of their head, the movement of their paw, the movement of their eyelids. How do they move their eyes in response to different things? And we could start to extract all of this information to get a general sense of not just whether the animal responds, but the quality of its response, the way that the animal responds. And this led to just a very, very simple analysis here, where when the animal experiences something that they find to not be painful, they feel the stimulus, they pause for a few moments, they turn their head to look at the stimulus as if, why did something just touch me? And then they'll move their paw to move it away from whatever that stimulus was. So it's innocuous. Like, I don't really care what that thing is. I'll hold it up my paw in the air a little while, and then I'll just put it right back down. But if they're experiencing something that's more painful, that they do not like, that's noxious, then what we end up seeing is that the animal moves its paw immediately because whatever is touching it doesn't like that. It's got sunburnt skin or something along those lines. And so once to get that paw out of the way because it's not sure what might be attacking it. And then the animal moves its head to then take a look at what is actually occurring. And at the same time, it's holding its paw up in the air for a little bit longer. It's guarding its paw because it's like, I don't know what just touched me. I didn't like that. And I want to know what's going on. And then we also see other little moments and other little behavioral syllables. The animals, and when they're experiencing something that's a little bit more painful, their eyes will grimace. They'll kind of squint their eyes a little bit. They'll jump up in the air. They'll shake their paws like, oh, what was that? Jeez, what just happened to me? And what that allows us to do is to create this range of responses that when we can analyze these things, we can say, well, if there's a decrease in the amount of time that the animal is moving its paw or the speed of the animal's paw, then that would mean that the pain therapeutic, this potential pain therapeutic, is decreasing the sensitivity that the animal's experiencing. And so, going back to this idea of whether or not high-speed imaging can help differentiate the extent of an animal's painful experience, we're able to find these different things to measure, including height of the animal's paw. So if the animal's really feeling pain, then the animal's going to move its paw really, really fast. And you can imagine if I take a paintbrush and the animal's in a state of pain, then that paw will now move a whole lot faster. It'll move a whole lot higher. And then you'll start to also experience specific behavioral syllables, just as the animal might jump, the animal might shake its paw, the animal might guard its paw, or it might squint its eye. And we can take all of that and do computational modeling, statistical modeling, and a machine learning algorithm to essentially create what we've coined as a mouse pain scale. On the y-axis right here is the amount of pain the animal experiences, and then on the x-axis is different types of stimuli that we can expose the animals to. And we find that the more innocuous stimulus is going to cause a much lower value on this, what we call as principal component score, or our pain scale. And then as something becomes more and more intense, then we can see that this goes up to a higher level. And what this allows us to do is to not just test pain therapeutics more effectively, to say like, okay, this thing is actually really changing, again, not just the response, hey, they felt it, or hey, they didn't feel it, but really changing the quality of that response. We can then apply this to other questions in the pain research world of how does pain circuitry, or how do the neurons that are responsible for pain function? How do they become dysfunctional, and how are they wired? And so for one example of applying this mouse pain scale to a question in pain research is that we know that there's these different populations of sensory neurons that live inside of our skin, all over our body. And there was a time when we thought that there were these two different classes. One is called MRGD neurons, another one's called TRPV1 neurons. And we had the assumption that both of those neurons were pain neurons, were involved in pain processing. But by putting our analysis to the test using these techniques called optogenetics, where we can activate the neurons with light, it's almost like science fiction, but we shine a blue light onto the neurons or onto the paw, and then we can activate those specific types of neurons, we can then examine what the behavior looks like under those circumstances. And what we found was that if we shine this blue light onto an animal's paw and we activate the neurons that make the animal think it's experiencing spiciness, basically hot pepper. They're called TRPV1 neurons. And we shine that blue light. So again, the animal's not being poked or anything like that. It's just we're activating those neurons very, very momentarily. This is slow motion video. We can see the animals get stimulated on his paw, shakes his paw, and it's like, oh, stop touching me, stop touching me. I don't really like that. But when we take this other class of neurons that the field has always thought were pain neurons, and we do the same exact thing. So this again, slow motion, we're shining, we're activating these quote unquote pain neurons. We can see that the animal still responds, but it just lifts it up, puts it back down, as if nothing is bothering it whatsoever. So it allows us to start to then really piece apart what is the actual internal experience. If we were just relying on the animal responded or the animal did not respond, then it would become really challenging for us to, or it would be impossible to be able to differentiate these two different types of neurons in the skin. And through that, the closer we get to understanding the neurobiology of pain, the easier it's going to be for us to be able to find new ways to treat that pain in the patient population. So we're also expanding this, and this is a paper that's come out very recently. The preprint has been published, and it's going through the peer review process right now, in collaboration with the Wimmer Lab at Temple University and the Abdul Sabor Lab over at the University of Pennsylvania. And we have 3 Rutgers candidate students who are working on this project. Bobby, Megan, and Kiyoshi is working on a side project that's related to this with the same content from it. But we've been able to expand this mouse pain scale to rats, and we see similarly, just like the mice, we can use this scale to also accurately assess the pain that a rat is experiencing. And why do you care about rats versus mice? It's just that some researchers use rats for certain types of studies, and then some researchers use mice for other types of studies. And so they had their pros and cons of what animal species that you want to use in your particular lab. But the Wimmer Lab is really interested in exploring how morphine-sired animals. So these are offspring, male offspring of fathers who have had exposure to morphine, or chronic exposure to morphine. How does the pain sensitivity of those offspring change when they're not exposed? They're naive. They've never been exposed to morphine before. How does your father being exposed to chronic levels of morphine affect his offspring? And using this technique, we've been able to find a slight nuance that demonstrates that the offspring are just ever so slightly more sensitive to morphine. So these individuals or these rats have never experienced morphine exposure, but because their father has experienced that exposure, now they're a little bit more sensitive. What does that mean for a patient population? That means that if they're a little bit more sensitive to morphine, then if they come in as a chronic pain patient, a pain doctor can prescribe a lower dose of morphine or of an opioid for their chronic pain treatment. So it allows us to be able to be a little bit more informed of decreasing the risk a pain patient might experience by being exposed to opioids. And right now, too, on campus, really being driven by Sherrick, Ubi, and Jenny, this work we're also expanding it to fruit flies. And why fruit flies? Again, each animal model there's pros and cons to using it to study different types of questions in the chronic pain world. One of the pros of fruit flies is that they're incredibly inexpensive. They're very, very cheap. So like it doesn't cost like anything to basically have a colony of flies in your lab. Whereas for mice, it ends up being a lot of money because you have to take care of them, you got to feed them, you got to make sure that they're entertained, that they're having a good time. So it ends up being much more expensive. So it's very, very cheap to run it for fruit flies. But we're doing a similar thing. These are videos from the Galco lab and also the Mathis lab of identifying or using machine learning algorithms to track their behavior, their pain-related behavior, with the hope that we can create also a fruit fly pain scale that will help us answer certain questions in chronic pain using fruit flies. And right now, Sherrick Khan, who's a Mark Fellow on campus, is exploring the intersection of sleep and pain. How does loss of sleep affect your experience of pain, and vice versa? How does chronic pain affect the loss of sleep? And there's multiple ways that feed forward mechanism can occur. And the two that we're really exploring and are interested in is how anxiety plays into that, and also how this mechanistic change in the connections between neurons called synaptic scaling contributes to that phenomenon. So if we go back to that first thing and think about how this pain story contributes to this big challenge in the pain field or in neuroscience in general, remember that we have these amazing technologies to be able to answer questions of wiring and function and all sorts of stuff, but we're still focused on a very rudimentary way to measure and analyze and assess the ultimate outcome, which is behavior, because nervous systems create behavior in our world. That's the whole feed forward thing. You have a sensory world that you're experiencing, your brain, your nervous system integrates all that information, and then it prepares a motor output of you changing your behavior, you doing something in the outside world. So with the pain, at least, we're hoping that what we're doing is we're improving this by providing an objective interpretation of the behavior of these animals, all with the goal of trying to find better methodology for the way that we test new pain therapeutics so that we can increase our success when we say that this drug, it works in animals, and we're pretty sure it's probably going to do well in humans as well. So that is really the core of all this. So I'm just going to wrap up my talk right there. I'm happy to answer any questions at all. I want to thank collaborators, Matt Wimmer's lab over at Tufts University, Ishmael Dusabor over, and also Wen-Chin Liu at the University of Pennsylvania. Funding is Rutgers Provost Fund, the NIH Mark U. Starr Fellowship, Population Health Faculty Professional Development Grant, the NIH Aracta K-12, which trained a lot of my stuff when I was a postdoc and continues to fund some of the research and teaching activities here on our campus, and then also collaborators and students at Rutgers Camden. Because again, the student population here at Rutgers Camden is really, really exciting, really, really interesting, and they do all this work. All of my work that I do now is all based on undergraduates. So if you are an undergraduate, reach out to me. I'm always looking to recruit more really, really good undergraduates. But uniquely, my lab, my research is driven by undergraduates. And you can find me on Twitter at NeuronNate or on my website, neuronate.com. Really easy to remember. By all means, you can reach out to me with any questions you might have. about this work, about anything under the sun, always happy to answer them. So thank you again. I really appreciate the time and having the opportunity to give a presentation in this lecture series, and I'll take some questions now.
Thank you, Dr. Freed. That was really wonderful and very interesting. I'm going to start out by asking you one of the questions that the audience sent in. And so the first question we have is, how do you convince an entire field to start measuring pain differently? It seems like it might be an uphill battle.
Yeah, so, if we go back to this idea of, what are the major ways that this field studies pain? We have 3 different behavioral classes, and most people are using this reflex-based assay. And again, because it's easy to do, it's fast, it's a really great way to get an assessment of rodents' experience pain or whether pain therapeutics working. So it is an uphill battle to work with the field and say, hey, like it's okay that you're doing that, but just so you know, like there's this other way to do it. But the challenge comes into play is because that other way to do it is just like trying to teach somebody to do something new. And if you think that what you've been doing for decades has been perfectly fine, like why make a modification? And really the way to address that, the way to do that is going to be to make it easier to do, to make it, to provide protocols so that anybody can pick up this thing and start using it in their lab. We have done that. We published recently an exact step-by-step protocol to make it easier to adopt it, and also just getting the message out to just say like, hey, listen, like we really need to rethink the way that we're using behavior to answer different questions because we're not using exact tools, and ultimately we're wasting a ton of money. So we need to increase awareness that there's another way to be able to do this.
Thank you, Dr. Freed. The next question we have is, it appears to be an efficacy issue when making the transition from a mouse model to the human model. How can the newly proposed pain model help bridge the gap in measuring pain tolerance variants that are similar to human tolerance levels?
Yeah, so I guess my answer to that would be that we need to make sure that everything that we do is clinically relevant. And I say that because actually Matt Wimmer's group, who's pioneering this work of the epigenetic transgenerational impact of morphine exposure, I'll scan down to his group right here, Matt Wimmer's group over at Temple University. His work is looking at low dose exposure to morphine and its effects on the progeny and also on the individual rat that's being exposed to that low dose. And the reason why he's using low dose is because most of the research has been really focused on high dose. And the reality is the realistic experience of the general population that might be exposed to morphine or chronic opioid use, it's really happening at a lower dose. You're using lower dose over several days, over several years, several months. And what he's trying to do is make sure that that the doses that he's using to answer the questions in addiction really are clinically translatable, that they are the doses that you would actually experience in the general population. And too often, I think researchers end up using clinically not very relevant methodology to model something that they see in humans. So the answer to that is just basically trying to make sure that whatever we're doing, whether we're measuring, whether we're inducing something or we're asking a certain question, that it's still clinically relevant, it's still clinically translatable in terms of the methods that we're using to approach it.
Okay, our next question is that all pain is definitely not the same. So how is it that you can study specific types of pain in mice? For example, like a headache is different, obviously, than fibromyalgia and things like that.
Yeah, so that's a great question. There are, like I said before, that there's these different ways to measure different types of pain in an animal. You can poke them, you can poke them on the paw, and you're basically getting an assessment of like how sensitive is their paw. You poke them on the tail, how sensitive is their tail. You can poke them on the head and see how sensitive their head or their forepaws are. But what it comes down to is making sure that we're developing models, quote unquote, models of different types of pain. And so we know that not all types of pain are the same in humans, that if I give an opioid for your lower back pain, maybe that would work. But actually, if I give an opioid to a headache patient, it'll make their headaches even worse. And so we know that there's different systems that are working for different types of pain. And so when we want to study one type of pain versus another type of pain in rodents, we need to make sure that we are modeling it in a physiologically relevant way so that we're asking questions not just in general about pain itself, but about the specific type of clinical phenomenon that we're seeing. So at the end of the day, it just comes down to making sure that we're inducing or we're modeling the human experience as close as we can. It can't be perfect, obviously. Rats, they're not humans, but we need to make it so that when we're asking questions about fibromyalgia or about migraine or lower back pain, that the animal does in fact have or something similar to fibromyalgia, migraine, or lower back pain. That's a great question.
Thank you, Dr. Freed. Our next question is from an undergraduate who is interested in getting her foot in the door in neuroscience. So what kind of recommendations do you have for students who are looking to get into this kind of field of study?
So that's a great question too. If you are interested in pursuing this, first off, kudos to you because it's a great field. I really enjoyed it. So you're going to be starting on a really fun academic journey. Neuroscience, the reason I ended up getting into it is because I thought to myself, I'm interested in becoming a scientist. What field should I go into? And I thought to myself, well, what is it that I talk about on a Friday night with friends? And it ended up being the human experience. It ended up being psychology, and ended up being, how do brains function? How do we store memories? And that led me to this world of neuroscience. But ultimately, how do you actually get into that? You do a PhD. Nice thing about a PhD is they're free, at least in the biomedical sciences. So if you want to pursue a neuroscience PhD after your time as an undergraduate here, it's not only free, but they actually pay you money. It's like a $32,000 a year job, basically for 5 years. And that's how you go into that field to be able to make an impact in that field. And how do you get to that PhD? The way you get to that PhD is you get research experience. As an undergraduate, I recommend everybody reach out to faculty members to get their foot in the door, to get some type of experience, even if it's something that isn't neuroscience related. Any type of research is going to help you, convey to a PhD admittance committee that you have thought about doing research. You know how to ask research questions, even if they're not exactly related to neuroscience. So my advice to you is just get yourself into a lab. And it doesn't have to be just neuroscience. Get yourself into any type of lab. And then also don't just look at Rutgers-Camden faculty. We have a lot of students. We have a limited number of faculty members. There's always opportunities for you to get research experience, but look outside of Rutgers-Camden. Look at Rowan. Look at Thomas Jefferson University. Look at Drexel. Look at Penn. Look at Temple. All of those research universities, they will accept students from other universities to come and volunteer in their lab. So there's a lot of great faculty members here, but if you have some other interest, don't be hesitant to just send a cold call email to a faculty member somewhere else. Not that I'm trying to tell students to go elsewhere, but there's a lot of resources. And at the end of the day, if you come out of your undergrad degree and you haven't gotten some sort of research experience or some sort of experience in the field, then GPAs don't get you everything. You really need to make sure you get that experience. That would be my suggestion. And then ultimately too, if you're not able to get it as an undergrad for some reason, look for lab tech positions as your entry-level job that you would get. Lab tech positions in any research environment will get your foot in the door so that you can apply for a PhD and then have that necessary experience to do well and be accepted.
Great. To kind of piggyback on that question, you've noted in your presentation the unique student population at Rutgers-Camden. What have you learned from working with them?
Well, one of the things that I've learned is that there are specific challenges that I've met when I'm coming from my low-income background of not being prepared in college or not knowing how, like, what we call the hidden curriculum, how to navigate getting your foot into the door of how to work office hours. I recognize that a lot of students here at Rutgers-Camden, because they are pioneers in their family, they're first generation, a lot of them are first generation low-income students, like myself. that there are these nuanced challenges that students will face. And I think one of the really pressing ones that I've noticed is that just because a student can't spend extra time in your lab working on a project does not mean that they're not passionate about the science. They may be, just like I was, balancing another job. They might not be able to sacrifice, the 15 hours a week to make progress on a project in your lab, and it has nothing to do with their interest or their excitement. It has to do with these are struggles that a lot of students face. And what I want to do is to try to modify curriculum, modify the culture, modify the systems that we have that bring students into a research world so that we can increase the opportunity for students that might be facing some of these challenges or struggles. Because everything from the imposter syndrome that I experienced, the limited time that I had when I was an undergrad, all of those things contribute to making it harder for somebody from a low SES background to make a life in this space. But for those students, find somebody who can understand that experience and just chat with them. It all comes together when you start to find more people to add to your mosaic of mentorship to create a lot of voices that can help guide you from step to step.
So the next question is shifting back a bit towards measuring pain. And so the question is, though more expensive, would it be easier to measure pain in larger animals such as monkeys, rabbits, or cats?
Yeah, so it actually becomes not just a financial thing. It's one of these, yes, it's going to be more money to do that. And does a primate brain have more similarities to a human brain? Yeah, there's going to be more similarities there. So things that you find in a primate are going to be a little bit more translatable to a human than things that you find in the brain of a fruit fly. But the field at large has sort of settled on, and I say field at large, I say like neuroscience in general, or just like all of biomedical sciences, has settled on specific animal models that are the most commonly used. And once they settled on that, then all of the genetic tools, like the tools that I mentioned about neuronal tract tracing and genetically encoded calcium indicators, all these special tools, they've been developed in mice primarily. And so if you are somebody that's asking a question that's very translatable and you're like, I have the extra money, I want to work with primates, that might be more translatable, but then you're also not going to have access to the genetic tools that are developed in mice. And the reason I say this is because you can't just take those tools and then apply them to primates. You have to use those tools in the thing that they were developed in, mice. And so it's not just a cost thing, but it's also a decision of, well, I need to ask this particular type of question, and it's not possible for me to ask this particular type of question in a primate, versus it is possible to answer that kind of question in a mouse because I have the right tools. So whenever a scientist kind of sits down and they say like, all right, this is the field that I want to go into, or this type of research question that I want to ask, they have to make the decision of these are all the models that are possible to use, and they each come with their pros and cons. Which one am I going to use? Think of it like, when you're making the decision of whether or not to get into the Google Android ecosystem or get into BlackBerry ecosystem. BlackBerry ecosystem might do a lot of great things, but it certainly doesn't work as well as an Android phone does for certain aspects of your life. And there's just way more stuff that's been developed on an Android than there has been on a BlackBerry. No offense to people who still use BlackBerry.
So I think we have time for maybe just one or two more questions. So the next one I'm going to ask is about New Jersey's legalization of cannabis. So do you believe that might be a potential avenue for moving away from opioids?
Yeah, so the challenge with it is that there is a lot of studies that have demonstrated how the cannabinoid system interacts with and can be utilized to treat chronic pain, certain types of chronic pain. But it's still in its infancy because there's been a lot of challenges to being able to study the effects of cannabis on these pain systems. So we know a little bit, and it's certainly a lot of promising information. But the questions of, what is safe how to use it in a safe way. What types of pain will it work for? Will cannabis work for migraine versus lower back pain, or vice versa? Will it only work for, neuropathic pain versus just general post-operative pain? So the questions basically still need to be answered. And so cannabis, with its legalization, will certainly open up more opportunity to perform these studies to, again, find what is it going to be used for effectively and in a safe way. What is the best way to approach it?
Okay, and I think we have time for just one more question. And so this one is, your work helps shift us from largely subjective assays in animals to more objective metrics. To look at the human setting, are our metrics with people going to be able to make that same shift to more objective measures of the experience of pain?
Yeah, this is a really good question, because right now there is a huge ethical question of what do we use to assess pain in humans. We use surveys. We ask them, what's your pain experience? But there's this whole world of research that's trying to find more objective ways to measure pain so that they can go in and they can measure a biomarker in your blood, or they can put an EEG cap on your head and then measure the pain, activity within your brain. And there is a lot of advances that are developing these quote unquote objective ways to measure pain in humans. But they're not perfect. And I don't anticipate them to ever be perfect. They will be just one other thing that can help a pain doctor understand the pain of a patient so that you can then better treat them. Because you can imagine that if they're not perfect and they don't always, like, let's say they're 98% of the time they can measure the amount of pain that somebody has, but then 2% of the time the pain measurement is inaccurate. If you are relying on those things, that means 2% of those patients who are experiencing pain are not being picked up by this device. And so as the physician, if you're only relying on that and you're not talking to the patient, then you can get into a murky place of saying that the patient is lying to you. And that ends up being an ethical quandary, because although you have this objective measurement, by not taking what their own personal experiences of that pain, if you're not taking that into account, then you're bypassing patients that really might need a stronger level of pain treatment. And you can also imagine too that the brain signal that you're measuring is only like the amount of pain, like the level of pain your brain is experiencing. But maybe you as an individual have more sensitivity to that same level of pain. So the brain says that there's a level of pain, level of 5, but then your emotional experience is saying, like, I can't stand, I can't deal with the level of 5. It's so painful, it's so bothersome, and it's affecting my daily activities. Then you can imagine how that would create this challenge of how to treat the pain patient. So there are objective ways that people are measuring and are developing, but we'll always have to look at it as a barrage of ways, multiple metrics, to be able to assess how should we actually work with the patient.
This is Dean Marcatello once again, and I want to thank Nathan Freed for that terrific talk and the questions from participants as well. And want to thank you for attending. And I would like at this point to turn the microphone, as it were, over to Mary Claire Venuto, who has a final message for us today.
Thank you, Dean Marcatello. On behalf of the Faculty of Arts and Sciences Camden and the Rutgers University Alumni Association, I want to thank Dr. Freed for presenting on this important topic, which touches so many lives. And I want to thank all of you for being with us today. Everyone will be receiving a follow-up email from us shortly, which will include a survey to provide feedback. As Dean Marcatello said, this is the last event in the Scarlet Scholars series this academic year, but we'll be starting up again in the fall with a great lineup of faculty. In the meantime, if you're interested in hearing more of fascinating virtual programs, please visit ouralumni.com to see all of our upcoming events. Please take care, everyone. We hope to see you at a future event soon. Thank you so much.